Heat waves, drought, tornadoes, hurricanes, floods, blizzards, bitter cold. Extreme weather has an incredible impact on people across the globe. On Mount Washington, our scientists brave some of the worst weather on the planet to improve our understanding of our warming world. All right, welcome everyone to Mount Washington Observatory Science in the Mountains lecture series. My name is Brian Fitzgerald. I'm the Director of Education here for Mount Washington Observatory. So glad that all of you could join both virtually and also in the room here as well. So thank you for coming. Thanks everybody. Really excited for tonight's talk tonight. We are fortunate enough to have a number of staff and interns here at the observatory who are going to be presenting all about current research activities at the observatory. So joining us tonight will be Summit Weather Operations Manager Mike Carmon, who's in the room here tonight. Online observer, brand new observer, Ryan Haas will join us. And then we'll have interns Madelynn Smith, Max Sasser, and Amber Stokes, who's here with us in person as well tonight. So thanks everybody for joining. If you're not already familiar with the mission of the observatory, so we are a nonprofit member-supported organization with a mission to support and advance the understanding of the forces that create Earth's weather and climate. The way that we do that, many of you may know, is by operating around-the-clock weather operations on the summit of Mount Washington, which we've been doing since 1932. And in addition to that, we conduct research, which you'll hear all about tonight, as well as developing and offering innovative educational programs. If you have questions tonight for tonight's speaker, certainly those of you in the room here tonight, by all means, we'll save some time for questions at the end. So make sure you hold on to those questions. For folks who are joining on Zoom, there's a Q&A button that you'll find in your toolbar as well. And that's where you can submit your questions. We'll make sure to have time at the end there to get to as many as possible. If you'd like to join us, if you're, say, joining us and watching this as a recording after the fact, you can sign up for programs like these or join in person for future in-person programs. You can learn all about those at mountwashington.org/education. Alrighty, so what I'm going to do here is so that everyone in the room can see this as well. If you're joining on Zoom, we are going to have some poll questions for you. And so I am going to launch those here in just as soon as I can actually see this. And we're going to go ahead and launch it. So for tonight's questions, and this is going to be hard for me to see a little bit, the first question we have here is just, plainly speaking, where are you joining from tonight? I'm assuming a fair amount of you in the room here are joining from locally, though many of you could be from further afield I'm seeing in the room here. Well, for those of you online, curious if you're from a state within New England, perhaps outside New England, perhaps outside the country as well. So curious about that. The first trivia question, because each of our presenters tonight have provided a nice little trivia question here. We'll see if we can get the answer to. The first one being, and I'm sorry, I'll have to take this away from folks in the room to see, just so I can actually read it to you. The first question being, one of the projects featured tonight has investigations within a certain climatological parameter called CAPE, C-A-P-E. What does CAPE stand for? Is it convective available potential energy? Is it conductive actual potential energy? Is it corrected annular potential energy? Good luck. Next one here. Which of the following environmental factors plays the biggest role in the process of leaves changing color in the fall? Is it cool temperatures? Is it rainfall totals? Is it wind speeds? Or is it shorter days? Think of that.
Can you repeat that question?
Yeah. Which of the following environmental factors plays the biggest role in the process of leaves changing colors in the fall? So is it temperature, precipitation, wind speeds, or day length? Is, I guess, another way to think on those. So think about that. Next, What are the two primary pressure systems that define the NAO? This is not an easy one here. This is the North Atlantic Oscillation for you weather buffs out there. Is it the Icelandic low and the Bermuda high? Is it the Icelandic low and the Azores high? Is it the Bermuda low and the Icelandic high? Or is it the Bermuda low and the Icelandic high pressure systems? I'm not going to read that one again. It's either you know that one or you don't, is my guess. And then the last one here is, what is the predominant wind direction for the most extreme precipitation days? So for the top 1% of all extreme precip events and the top 5% is one of the things we're going to hear about tonight. And are those wind directions generally the southwest and the northeast? Is it the southeast and the east? Is it the west and the southeast? Or is it the southeast and the west? Just a little flip there. What do you think the wind direction for the most extreme precipitation events typically come from? Don't even worry about those answers. Just think in your minds, for those in the room, what that may look like. So we'll go ahead. I think for folks online, unfortunately, I may have ended that poll much too soon. I'm not sure why that happened. My apologies to everyone joining via Zoom, but we will give them an opportunity. Let's see if I can actually launch this properly. Oh, it is there. Okay. Sorry, folks on Zoom. Go ahead, give yourselves a good minute or so. So again, where are you joining from tonight? What does CAPE stand for? What are the factors that play into the changing colors in the fall? What are the two primary pressure systems that define NAO? And then what is the predominant wind directions for the top 1% and 5% of extreme precipitation? So I'll see if give folks on Zoom a chance to participate if they would like here. It looks like the poll should be live. But if not, we'll just have to find out what the answers are to these questions, unless, I don't know, do we feel confident in the room here? Perhaps. All right, well, we'll not linger on that too long. Let's get to the good stuff for tonight. So without further ado, I would love to turn things over to our first speaker, who is going to share just a little bit of context and background on research and the intern program activities here. So I'd love to bring up our Summit Operations Director Manager here, Mike Carmon. Welcome, Mike. Let's see, hopefully I can get this shared for everybody here. So I will. I'm sorry, I gotta share this as well. Oh, all right, Mike, take it away.
Yep. Good evening, everyone. Again, like Brian mentioned, my name is Mike Carmon. I'm the Summit Weather Operations Manager for the Mount Washington Observatory. My job is multifaceted, and maybe one of the most rewarding parts about my job as a scientist, but also as an educator, is managing the Summit Internship Program. And you're going to hear from a couple of those interns this evening. So I'm going to give you just a little bit of context as far as what the program is all about. And the research projects that our interns are working on sort of put that in perspective as well. So as far as the internship program goes and the structure of it, our interns come from all sorts of different backgrounds. As you can imagine, of course, atmospheric scientists are sort of naturally drawn to the work that we do on Mount Washington. But that's not all. We have folks from general environmental science backgrounds, as well, participating in the internship program, and just the general physical sciences as well, physics, chemistry. We've had lots of different scientists with different backgrounds interning on top of Mount Washington. As far as where our interns are from, nationwide, we have interns joining us from all over the country, which is very exciting for us. Over this summer, we've had a couple interns from a little bit closer here in New England, but we've also had some from out west as well. And we have 4 new interns incoming in a couple weeks here, and none of them are from east of the Mississippi River. So our internship definitely draws quite a broad geographic audience, if you will, just the nature of Mount Washington and the world-renowned weather. And we have seasonal opportunities as well. We have three kind of internship seasons: winter, summer, and fall. This evening, you're going to hear from our summer interns who have been with us since approximately mid-May or so, working on the projects that you'll see. And they're working week on, week off, right alongside our weather observers. So, in addition to the research work that you'll see them presenting this evening, they're also helping out with summit operations, doing weather forecasting, communicating to the public about the observatory and its mission. And as far as just sort of overall goals of the internship program, of course, the big one is, giving interns real world experiences in an extreme weather environment. The summit of Mount Washington is a fully functioning weather station. It's also a workplace. So for a lot of interns, including myself, when I was an intern, it was my first sort of big person job, if you will. And for a lot of our interns, that's the case as well. So, they're in addition to learning how a weather station operates, they're just also learning how an office operates and what that looks like, of course, in a very unique environment. And of course, part of that operation support, like I mentioned, is helping out with our weather observations and our forecasting. Like I said, they're working right alongside our weather observers, learning from those experts that have been up there for a number of years. And then public engagement as well. So during the summertime in particular, as any of the four interns this evening can tell you, they've done a good amount of tours of our weather station, sort of educating the public about what we do when they do make it up to the summit. And then also other forms of public engagement as well, doing radio broadcasts with the forecasts that they're preparing. It's all wonderful experience for them. And then, of course, the kind of the feature part of the internship program we're talking about tonight is research. Mount Washington Observatory has a long-standing high-quality data set, in some cases going back to the 1930s. And so our interns are really leveraging that data in order to create meaningful projects with meaningful results. And as far as, the research project goals go there, um, first off, it's just familiarity with the research process, and as anyone who's done research can attest to, including our interns, it is a process. Everything from formulating hypotheses to doing lit reviews, data analysis, peer review, writing, editing, rewriting, all that fun stuff. It's a great learning experience for them. That data analysis is, again, using real world data. It's our data that we're collecting, and they're using that and analyzing it in real time. And addressing meaningful questions and challenges, as you'll see as they talk about this evening. And then they're being mentored by our seasoned observers. We have one kind of lead research observer on each shift that are helping mentor the interns, in addition to other scientific professionals as part of our science committee that mentor interns week to week, sort of help focus their projects, give them some sound expertise as they figure out the projects and the direction they're going to go with it. And of course, communicating as well the work that they're doing. Part of what they're doing this evening, of course, and in my opinion, science communication, we can't emphasize it enough how important it is to not only do meaningful research and meaningful science, but then turn around and educate the public about what you're doing. And with the proper context, the proper nuance, we're giving them lots of those opportunities to do so week to week, month to month as they work through their projects. And they're coming up with meaningful products. So it's papers, it's posters, it's other operational tools that can be used by the observatory. Some recent examples, we had an intern over the winter knee deep in research for a good 5 months. That's going to lead to a White Mountains Almanac that's going to be professionally published here very soon by the observatory. And then another one you'll hear about this evening actually is a phenology-based forecast model that will help the observers do some foliage forecasting come fall. So excited about that. Well, that's all from me. So I think it's time to dive into that research. So we can introduce intern, well now newest weather observer, Ryan Haas, who's going to talk to us about his project.
Hello, everyone. I'm Ryan Haas here, and yeah, let me just get my screen shared. Hopefully
Yeah, I'll stop
that
sharing.
works.
Then.
Can everyone see the slide there?
Not in the room just yet.
Might take a second.
All
Is
right.
it
Well,
is it
so for the folks in the room here, we can see it, and then folks who are online can see it as well. So Ryan, take it away. Thanks so much.
All right, perfect. So yeah, over the summer I investigated extreme precipitation climatology on Mount Washington. Um, so if we get into this slide here, yeah, so extreme precipitation, it's very important because understanding like when it generally happens and just extreme precipitation in general is very important because these events often bring very disruptive conditions, such as like flooding, slippery trails, avalanche dangers in the winter, especially if you're getting a ton of rain on top of snow. So it tends to be very high impact events when we have extreme precipitation. So that's why I wanted to investigate that this summer to understand like when we tend to have the most really intense precipitation events. So my main research questions are what is the climatology of extreme precipitation on Mount Washington? So that's like when does it typically happen? When do we tend to get the biggest events? Next question is what types of storms produce the most extreme precipitation days each season, whether that be like extratropical storms or like hurricanes. And then what storm tracks typically yield the most extreme precipitation days? So those are the main questions I set out to answer. So for this project, am defining extreme precipitation days as top 1% and top 5% of wet days. So that's just every day that has 0.01 inches of rain, just the top 1% of those events. And then also the top 5% of those days that have over 0.01 inches. And so I decided to examine extreme precipitation on a daily time scale because multi-day events often see the heaviest like precipitation rates concentrated on one day. So if you have like a 3 or 4 day extreme precipitation event, a lot of the times those a lot of that precipitation will fall on just one of those days. So that's why I am looking at extreme precipitation days in particular. Moving on to the next slide. So this is a look at the extreme precipitation day climatology. So how I would define an extreme precipitation day, like in this context, is the number of days that produced extreme precipitation totals. So for top 1% days, that threshold is 2.69 inches of rain. So if you got over 2.69 inches of rain in a day, that would be considered a top 1% precipitation day. And then for top 5%, it's about 1.5 inches of rain. So yeah, if we take a look at this plot on the right here, this is just a look at the number of top 1% and top 5% precipitation days by month. And you can see that we tend to have a bit of a peak in the fall months for both top 5% and top 1% days. So yeah, you can see in October that it really spikes. And for top 5% days, it's interesting that the spike happens earlier in the summer, but you don't really see the same spike in frequency in July, August, and September for top 1% days. So I thought that was a really interesting result. This figure all the way on the left here, this just shows the average intensity of top 1% and top 5% precipitation days. So this is just how much rain typically falls each month within extreme precipitation day. And you can see the peak is also in October. And then this plot on the top left, this shows just the total precipitation from top 5% and top 1% days. So this is just adding up all the precipitation from extreme precipitation days in each month. And you can see October, there's a clear peak. So definitely October is the month where we really get a lot of our extreme precipitation. So I also did a subjective analysis going through like WPC surface archives to come up with kind of a storm track climatology by month of when we typically have extreme precipitation days. So you can see that on this plot on the top right, this is showing the number of days with extreme precipitation by type of storm. So you can see extratropical storms, which are our typical storm systems. They really reign the most popular. We've only had a few hurricanes up here in the Northeast, but you can see that we have had a few cause extreme precipitation days up here, and this is specifically for top 1% events. And then this plot on the bottom here, this shows the monthly count of left versus right storm tracks. So left would be a storm track that tracked to pretty much to the west of Mount Washington, and then right would be sort of a nor'easter-like storm. that track to the right. And you can see storms tracking to the left or west of Mount Washington tend to produce more extreme precipitation days than ones tracking to the right, but that gap becomes a little bit narrower as we head into August, September, and October, where it's a much more even. But generally speaking, storms tracking to the left tend to produce the most extreme precipitation days. And of course, there were a few caveats to this. I only really looked at systems that were within 1,000 kilometers of Mount Washington, because if they're further than that, it's hard to really say that the precipitation was being caused by those storms. And then there were some cases where there were multiple low pressure systems close by. And when that was the case, I just used the closer and stronger low pressure system for my analysis when I was looking through the data. And then there's often other times when you have secondary cyclogenesis, which is when you have a low pressure system moving up, but then a secondary low pressure system forms like off the coast. And in those cases, I just classified the storm setup based on conditions during the heaviest precipitation, and that was determined by using historical radar data. So then I also decided to look at it more objectively. So I created wind rose plots using discussing like the prevailing wind direction on each extreme precipitation day. And that showed that a majority of the top one precipitation days featured southeasterly winds, hint for the trivia question. And while most top 5% precipitation days have westerly winds. So the answer to the trivia question would be D. So yeah, I also created plots showing whether the winds turn clockwise, counterclockwise, or remain neutral during an extreme precipitation day to help objectively determine storm tracks. So in this example here on the left, the winds right now are out of the south, but as that storm moves further to the north, the winds will shift out of the west. So that would be an example of a clockwise shift over the day. So that was just a way I did it. It's not perfect, but it was a way to look at it more objectively than just looking at WPC analysis maps. And then counterclockwise shifts suggest an east to right track. If you look on this example on the right here, this was a pretty strong nor'easter that we had that produced extreme precipitation, but you could see the winds are out of the east. And then as the storm moves north, they'll turn out of the north and then northwest, and that would be a counterclockwise track. So yeah, I found pretty much the slope by like unwrapping the hourly wind direction data, so that it didn't go, there wasn't any big jumps from like 0 degrees to 360 degrees. And then I just performed a linear regression of wind direction versus time for each extreme precipitation day, just to get another look of the storm tracks associated with extreme precipitation events. So moving on to the next slide here, this is the wind rose plots. So this is showing the prevailing wind direction during all the extreme precipitation days during each season. So for top one precipitation events, you can see that southeasterly winds really are dominant throughout. They're dominant throughout each of the seasons, where that's the most common wind track, or that's the most common wind direction. And you can see that 71 events had southeasterly winds for top 1% days, compared to much lower numbers in the other areas. So definitely southeasterly winds win out. And then for top 5%, it's interesting that actually westerly winds were a lot more dominant for those kind of less extreme precipitation events. Southeasterly winds were a close second, but westerly winds definitely won out in the summer and fall months. And then moving on to the last slide here, this is the objective analysis that I did with like wind direction shift during extreme precipitation days, where we were looking at clockwise, counterclockwise, and neutral. So for each precipitation event, I just looked at the wind direction each hour using our hourly data set. And then I performed a linear regression to find the slope. And if that slope was greater than 1, then it was a clockwise event. If it was between -1 and 1, it was a neutral event. And then if it was lower than -1, then it was counterclockwise. So you can see clockwise events, so storms tracking to the left, are definitely the most dominant, which lines up with the subjective analysis I showed earlier. But there's also plenty of counterclockwise and neutral events too, where the wind direction doesn't shift at all during the day, or doesn't shift much during the day. So that's pretty much all I have. Have some references here, and thank you very much. I hope you all enjoyed, and hopefully you all got that trivia question.
Thanks so much, Brian. I know we do have a couple questions that have popped up in the chat, and as people are thinking of more, certainly for those in the room, we'll store those away for a little bit later on. And then if you do have questions through Zoom, please feel free to keep those coming along. Ooh, thank you. Well, we'll go from there then. Thanks again, Ryan, and we'll transition up to the summit of Mount Washington, where we have our off-duty interns here who are presenting with us tonight. But then we still have interns on the summit who are carrying out their shift duties. So I'll turn it over to Max Sasser, who's going to present first from the summit. So take it away, Max, as soon as you're ready, and unmute when you want.
So hello from the summit. My research focused on convective activity and convective patterns in not only the White Mountain area, but also in the region of New England. So a very preliminary climatology so that other studies can build on that county mountain. So for the motivation or some context behind the research, thunderstorm activity has increased in the White Mountains in New England. We know this from observational data from 1935 to today. You can see through this red trend line that we have a steady increase in the number of thunderstorms that have occurred, or the number of days in which thunderstorms have occurred on the summit in the month of July on this plot right here. Secondly, the peak convective activity occurs during the June, July, August, or as we like to call it, meteorological JJA season. A changing climate favors an increase in the frequency of these convective events. This has been supported through multiple studies using global climate model projections. And then finally, those most noticeable changes in convective activity or any weather phenomena of that due to a changing climate is on those fringes of peak activity. So you know how I said that June, July, and August are our peaks of convective activity? Well, May and September are projected to be impacted the most through this and will have the most noticeable changes. So in order to study the environmental favorability of convection or thunderstorm activity in New England and the White Mountains, I looked at 4 different types of parameters that would be of interest for this. So first is our convective available potential energy, or CAPE. So for my trivia question, I asked what CAPE stood for, and that is exactly the answer. I believe I put A for that, convective available potential energy. The second parameter I looked at was 2-meter temperature, or temperature close to the surface. 2-meter dew point temperature, again, that's just the dew point temperature near the surface. And then a 0 to 6 kilometer bulk wind difference, which is basically taking 2 different wind vectors, one at the surface and one at 6 kilometers above, and taking that difference. That is our bulk wind difference. And I forgot to go into it, but CAPE is basically just the amount of potential energy that a bubble of air or a parcel of air has to rise without anything stopping it. So think of it kind of like, you know, having a pot on boiling water, and whenever you take that lid off, all that steam comes up. That's all that potential energy that's rising without any friction. I used 2 different data sets to look at the different parameters. The first is reanalysis data. Reanalysis data is basically almost like hypothetical observations, basically taking the surface observation network that we have and snapping those into grid points using a series of mathematical formulas. That's what our reanalysis data does. I use the insect reanalysis version 1 data set. The reason why I did that is because it has a 4-time daily observation run through. And as you can see on this figure right here, you can see all the various points where those hypothetical observations are coming in. And it has a 2.5-degree resolution, which worked perfectly for the amount of time that I had on this project. I had enough data without getting too thick in the mud for the summer. And then down here, I also used radio saw data or weather balloon data. The National Weather Service launches these balloons twice a day. And the nearest one to us is the Carmon National Weather Service Station. It is also one of the most reliable weather balloon launch sites in this region. So looking first, I'm not going to go through all the parameters just for the interest of time. However, I will go through Cape. This is from the reanalysis data set. So this moving image on the right shows the number of timestamps or number of observations at each location where Cape exceeded 100 joules per kilogram. 100 joules per kilogram, if you don't know anything about Cape, basically that's where we have a pretty good environment for even some cumulus clouds to develop. And so looking at each decade, the number of observations in which Cape exceeded 100 joules per kilogram. If you can see here, if you look at it long enough, you'll notice that from the 1950s to the 1980s, started off really high in the 50s and then kind of steadily declined in the 80s. And then in the 1980s, Cape started to steadily increase again. That is supported using this trend line here. This trend line is the 90th percentile of Cape values that occurred in the month of September. Remember, we're looking at the fringe of Cape activity, so I looked at September for this. As you can see, the peaks in Cape values from the 50s to the 80s also steadily decreased, and then from the 80s onwards steadily increased. So that's kind of the overarching trend that happened in the inset reanalysis data, and it's exactly what happened also with the radiosonde data, so it matched really well. As you can see here, I do not have data going back to the 50s with the radiosonde data because the data only went back to 1995. So instead what I did was instead of doing decades, I grouped the number of observations where Cape exceeded 100 joules per kilogram per 5-year groups. So as you can see here, from the mid-90s to the current, to 2024, we have had a pretty steady increase overall in the number of observations in which Cape exceeded 100 joules per kilogram. That's also consistent with what we can see in our 90th percentile or extreme values of Cape from 1995 to 2024. As you can see, we have some peaks that go steadily up. We have a really sharp increase in the year 2023, which was a pretty active year convective wise. It's not really certain whether we are able to conclude that we have, just we're going to have so many more years like this, or if this was just kind of more of an anomalous year. Of course, another future work could be to look at whether or not more years like that are going to happen in the future, or if we are going to have more of a peak similar to around 2030. So to kind of wrap it all up, what I found was not only Cape, but 2-year temperature, 2-year dew point also increased pretty steadily throughout the 1980s. Reanalysis data and radiosonde data had a moderate correlation, which is actually pretty good, a lot better than I had expected. And the correlation is a lot stronger in cases of very little or very widespread instability. So that worked really well. Finally, the wind shear or bulk wind difference remains constant, which indicates that convection may not become more organized. Basically, what more organized convection is, think like supercells or those multicellular systems. We're not going to be necessarily more of a conducive environment for those, but singular convective cells are definitely projected to increase based on the trends of Cape 2-year temperature, 2-year dew point temperature. So for some future work, we can investigate the relationship between these environmental parameters and convective phenomena type. More specifically, like looking at kind of doing a more of an objective analysis on categorizing different cases that have happened in the past 70 years and correlating those with the reanalysis data set to see if there's any noticeable trends with those. We could also investigate the relationship between an increase in Cape and the severity or magnitude of thunderstorms. Maybe that's how large the wind gust is or how large the hail is. And then finally, because I did not have enough space nor time to go into more of a finer resolution of reanalysis data, there is finer reanalysis data sets, such as the ERA 5, which is managed by the Euro model. So we could definitely run this all over again with a more finer resolution. And that's all I have for today. Thank you so much for listening, and I'll be happy to answer any questions.
All right, thank you so much, Max. I really appreciate that. I know, I think what we'll do next is actually have Amber present down here in the valley, and then we'll send it back up to Maddie or Madelynn to finish it off. So thank you so much. And again, for anyone who had questions, I know there's some great questions that have popped into the chat already. Please feel free to get those in on Zoom, and we'll try and get to as many of those as possible. So for the time being, though, before what we'll do is we'll bring things back over and down here to the valley in North Conway, and what we'll do is we'll introduce intern Amber Stokes, who will present on her project looking at the investigation of NAO's impact on extreme snowfall events on Mount Washington, which I know folks have already been asking about in the question. So without further ado, Amber, take it away. Hopefully I've shared all this. I think actually, my apologies, I think I do need to just share the screen so that everyone online can see it as well. And oops, sorry, I have this thing impeding. All right, should be good to go.
Okay, hello. This is my project that I did this summer looking at the NAO's impact on extreme snowfall events on Mount Washington. Yeah. Okay, so just as like general background, if you don't know what the NAO is, it's an interannual global teleconnection that's kind of split into two phases, and it takes place in the Atlantic Ocean. The positive phase correlates with having a stronger high and low pressure center in the Atlantic, specifically the Icelandic low and the Azores high, if you didn't know the trivia question. And the negative phase correlates with weaker centers. So the strong centers kind of act as like keeping the highway of the jet stream straight. But when you have weaker low pressure centers, the jet stream is able to bend more. So it has more of a blocking effect for anything moving across the Atlantic Ocean. So yeah. In my project, I was looking specifically to see if there was a statistically significant difference in the average snowfall days between the most positive and most negative NAO days. And I was also analyzing how the NAO influences the distribution of extreme snowfall on Mount Washington. So in terms of my methodology, I used pretty much three main methods: composite resampling, extreme value modeling, and influence of the covariant. So composite resampling is a method that I used initially the snowfall data from 1979 to 2023 from the Mount Washington records. And I took the top 3% of the events that were filtered out, and that ended up with 733 overall extreme snowfall events that were greater than or equal to 6.3 inches of snowfall. And the data was then filtered from October to April, which were the snowiest months on Mount Washington. And then I also took NAO indices for the 3 days prior and the 3 days after, and including the day of the snowfall event, to compile a 7-day average of the NAO indices. And so then I took the top 50 most positive and most negative values of the NAO of those indices that I collected. And so with the mean snowfall from each of the positive and negative NAO groups, I performed a Monte Carlo analysis, which was completed by randomly sampling 100 snowfall events without replacement, meaning when you took it out, you didn't put it back in, so the chance of it went down, and calculated the difference in those means. And I did the analysis 10,000 times using code, not on my own. So my second method was extreme value modeling, which used the same filtered top 3% snowfall events and the correlating NAO indices from October to April. And I categorized the data into 3 different NAO phases: a strong negative, neutral, and strong positive. And because the NAO indices goes between -1 and 1, that kind of split it up in the middle. And for each NAO phase, I use a filtered generalized extreme value model, or GEV model, to create a distribution. So when you do a GEV model, it gives you 3 different types of results: a location, which kind of shows you where the bulk of the data is located on the distribution; the scale, which shows how spread out the distribution is, and then the shape, which determines the tail and if there's any skewedness in your data. So the last method that I used was the influence of the covariant, which was more a background study. So I performed an initial climatology to show the snowfall data and the NAO indice correlations. And then I also made mean sea level pressure maps using the ECMWF's ERA5 reanalysis data to visually compare the effect of a positive and negative NAO phase in the ocean during my time frame. So you can see the picture on the left shows a positive NAO, and it's a pretty straight-ish line with where the jet stream is. And then when you have the negative NAO phase, there's that blocking that's happening. Okay, so in terms of my results, the first analysis that I did was the Monte Carlo. And so I found that while the negative NAO events appear to produce more snow on average, the difference is not really statistically robust. So you can see on this chart that the red line, which is right next to the blue line on the right, is still within that difference, the confidence interval, which is whether it's statistically significant or not. So because it's still inside, it means there's a possibility that it could have been a random occurrence. So we can't say that there's a positive correlation between them. So based on just mean values alone, not overall, but there is no strong evidence that the NAO phase controls the average snowfall that happens on Mount Washington. But again, that's just using mean values. In terms of my GEV analysis, the three parameters were location, scale, and shape. The location showed that it was highest when the NAO was strongly negative. So you can see that means that there's more extreme snowfall during the negative NAO phase. The scale was also larger during the negative NAO, which means there's greater variability in extreme snowfall. And because the shape is less negative, it indicates that there's a heavier upper tail for more extreme maximum snowfall events. So on this chart, the blue line, which is the shorter one, is the negative NAO. And because its peak is further like in the increased amount of snowfall, it means that there were more higher snowfall events that occurred than the negative or neutral, or the positive or neutral. And that is all I have. So thank you.
Lovely. All right. Thanks, Amber. Love that. I have some questions myself. I'm going to hold back. I will save those toward the end here because we do have one final presenter here for this evening. And so we're actually going to send it back up to the summit of Mount Washington once more and hand it off to Madelynn Smith here. And I will make sure that everyone can see you. I think everyone can see you just fine in the room here, and hopefully folks can see you okay in the room. Well, of course, I just got rid of you. All right, Maddie, I think you are all good to take it away. Go for it.
All right, awesome. Hi, everyone. My name is Madelynn, and I'm just going to go ahead and jump right into my research project this summer, which was forecasting fall foliage in Vermont, the role of meteorological factors in autumn phenology. So just some motivation, some background for my project. So if you weren't aware, Mount Washington Observatory is in partnership with RBG Radio Vermont, where we produce radio forecasts throughout the week exclusively for Radio Vermont. And now we've expanded our partnership to include fall foliage forecasts this coming fall, which is very exciting. And so the basis of my project was to kind of build a base for that, and to help observers out and provide some operational guidance. So with this project, I wanted to establish relevant meteorological factors that affected fall foliage. So I find trends between different weather patterns and different fall foliage performances. I'll also be referring to that as discusses. And to provide a foundation for future work, so this was primarily a literature-based study. I wanted to compile previous work done on fall phenology to provide a solid base for the observers here on Mount Washington, and to build reference material for future use for future interns. So we're going to go ahead and jump right in. We're going to give an overall fall climatology and phenology for at least the state of Vermont here. So on the left here, I have kind of a September-October timeline, which is about when fall foliage season occurs for New England. kind of the 3 different areas of Vermont that I have designated that have different climatology and that have different foliage periods. So we can see here on the right, I actually have a graphic, and go ahead and watch it a couple times because I know it can be a little hard to see, but this kind of just shows the progression of fall foliage as we go throughout the year. Typically, we start at earliest in mid-September in higher elevations and in the Northeast Kingdom part of Vermont. And as the month goes by, leaves start turning in part of the central and eastern Vermont and the latest in Champlain Valley. And usually peak activity, typically, is during the month of October, going chronologically between Northeast Kingdom, Central East Vermont, and the Champlain Valley, with all foliage typically ending by the end of October. Examining, so now we're going to look at some of the meteorological trends and factors that impact fall foliage. So timing is the one I want to focus on first. So 2 big ones: precipitation that impacts soil moisture and temperature. So drier soil, less precipitation for a drought typically leads to an earlier foliage season. Meanwhile, while wetter soil where we've had more precipitation typically leads to a later foliage season. We get the temperature. Hotter summers and fall temperatures lead to a later foliage season, while cooler summer and fall temperatures lead to an earlier fall foliage season. If you take a look here, you do kind of see that these can contradict with each other. So if we had like a dry but warm fall, that could definitely contradict to each other. So it's definitely still a bit of a research to figure out which factor has the most impact.
Hey, Maddie, would it be possible to share using the Stream Deck to make that full screen, just so we can appreciate, maybe, yeah, thanks, Amy. Yeah, that helps a little bit, at least for us and hopefully for those online, because you got a lot of awesome parameters in there. So anyway, sorry to interrupt.
No worries at all. It's just 1 second, make sure we get that fixed for you all. Is that good? Yes. All right, is that working for you, Brian?
Yeah, that looked much better.
All right, awesome. Yeah, so just diving back into intensity. So not only do meteorological factors have a play on the timing of fall foliage season, but they also have a play on how intense a given season could be. So a cooler summer plus cooler temperatures in early fall lead to more vibrant colors, while warmer fall to minimum temperatures mean more dull colors. And more brighter days with less cloud coverage typically means more vibrant colors, as well. So you can see the different factors that play into fall foliage here, but even those impacts can vary by species. So here I have the 5 most common deciduous tree species in Vermont. And if you take a look here, we can actually see not only do impacts vary from different species, from maples to white ashes, but there's also some interspecies variability between the paper and yellow birch, which can make forecasting fall foliage a little bit tricky, but it's pretty cool to see how that plays out. And so just for some conclusions, so overall, meteorological factors play a secondary role in autumn-senescence. At the end of the day, it is the shortening of days, the changing photo period. That is the primary driver for leaves change color in fall. That was the trivia question. Dad's listening out for that. That is why foliage season is around the same time period every year, give or take a few weeks, depending on the meteorological factors that I discussed today. So we talked about what plays into fall foliage. So what about for this season? So it's too early to make any definite conclusions. We want to see how early fall temperatures and precipitation play out. However, just looking at long-term forecasts from the Climate Prediction Center, we can see that they are predicting above average temperatures for New England, which could indicate a potential delay in the onset of peak times for this season. So, but this can change depending on how early fall plays out. And local weather patterns over the next month heading into fall will reveal more about this year's foliage season. So that will be it for me. Thank you so much for joining me today.
Thanks, Madelynn. I really appreciate that. And for those of you who are both in the room here and online, I'm going to go ahead and make sure that we can see everyone once again. But I'm really curious for folks both in the room here and online. I know we already have some questions. And perhaps there, in case you didn't get a good chance to see any of the images you had before, I would love to open up to questions. But before we get there, I know we had one question online that I wanted to go to, which is just real quick because I think Mike gave a really nice introduction at the beginning, just in terms of like the broad variety of backgrounds that we see from all of you, particularly our interns. I'm curious if maybe starting with Amber in the room here. Amber, if you want to come over, would really love to just hear maybe a little bit more about your individual backgrounds, like, you know, where you went to school, where you grew up, perhaps why you got into this sort of crazy situation to come intern for the observatory. So I don't know, Amber, if you wanted to share a little bit first and come on over.
Yeah, so I,
So sorry.
um,
Okay.
so I am originally from Central Maine, Bangor area. I grew up there. I was born and raised there. I go to school currently at the University of Delaware. I will be a senior in the fall in a couple of weeks. I have always loved science. I've always wanted to study physical science. Meteorology was just like my calling, I guess you could say. And in terms of coming to Mount Washington, I grew up going to many different national parks across the country. I live very close to Acadia National Park, so I've been there many times. I've come to the White Mountains before. So I was really enticed by being able to spend a lot of time here doing something that I love and a topic that I really want to continue to study when I grow up, I guess. I'm not.
Thanks, Amber. Appreciate that. I don't know if I want to turn it over maybe up to the summit next. If you know, between Max and Madelynn, where are you guys from? What are you studying? How'd you get here?
Yeah, so I'm originally from Texas, and though it's not a competition, I am the intern who did kind of drive the furthest to get here. I just graduated from the University of Oklahoma with my bachelor's in meteorology. I'm actually going back after this internship to pursue my master's in data science at the University of Oklahoma. And you know, I've always been interested in the weather. I learned about it in school, and it got me hooked onto the weather. And how I found about this internship was actually, I know my mom's watching on the stream, so I'll shout out to her. She was the one who actually found this on the internet and encouraged me to apply, and I'm glad she did, because I was able to run into this wonderful crew and have this amazing experience up here on the summit this summer.
What about you, Madelynn?
Yeah, so I grew up in North Carolina. I recently graduated from UNC Charlotte with my bachelor's in meteorology and earth sciences. After this, I will be going back to school to get my degree in emergency and disaster management, which is something I'm really looking forward to. And yeah, I guess I've always just loved weather growing up in the South, and especially in North Carolina, we're prone to a lot of tropical systems coming in. And so that always really fascinated me, and that just kind of blossomed into something I wanted to do as a career. And how I heard about this internship was pretty funny. I was looking online for things post-grad, and I came along this, and I said to myself, as someone who had never been further north than New York before, I was like, oh man, I'm gonna apply, but like, there's no way I'm gonna move to New Hampshire, right? And well, here I am, and I'm really happy I accepted. So
Well, we're glad to have you too, Madelynn. Thanks so much. And turn it over last but not least to Ryan. How'd you get here?
Yeah, so I've been into weather my whole life, ever since I was a kid, and just intense thunderstorms always got me very excited. We had a really good one last night, so yeah, it's still the love is still there. And yeah, so then I pursued my bachelor's degree in meteorology at University of Miami. So I went way down south, and then I'm like, I missed the season, so I went up to UAlbany for a master's degree in applied atmospheric science. And I've always known about Mount Washington because grew up skiing in the area at Attitash and Wildcat. So I've always heard about the extreme weather here. And then things just opened up, and I was like, yeah, I'm going to apply for this. And now I'm a night weather observer at Mount Washington. So I'm super excited to really get into my career here at the most extreme weather, at the place with the most extreme weather on Earth. So very exciting, and very excited for the future.
That's great. Thanks, Ryan. Yeah, you have followed in the footsteps of many observers who oftentimes start their careers as interns. A couple of us in the room here. Curious, any questions from folks here in the room as well that bubble up? Want to give you an opportunity. There are lots of questions online too, but if there's anything here, yeah.
Specifically to Amber, loved your presentation. I also have a background in statistical studies. I really like the way that you explain things in everyday language, what your data told you, and what more importantly, you couldn't infer. My only question is, after all those compliments, what was your confidence alpha that you used for your testing? You said it didn't fall, so it could have been due to change. Pardon?
95%.
Okay. Thanks.
So for those online who may not have heard the question, it was glowing praise for all of Amber's statistical work. And I'm going to badly paraphrase the rest of the question now, which is just a question of your sort of the confidence interval that you had there. And 95% was the confidence interval that you went with. Excellent. For some questions that have popped up on here, I know there are quite a few folks again, I guess maybe put you on the spot a little bit, Madelynn, but I think folks were just so caught in a nice way with the footage that you provided with some of the maps and images that are there. Do you have a sense of both where folks might be able to see that maybe in the shorter term or what that could potentially look like in the future? Because I know I'm super curious and would love to see your work and continuing work in a visual format. And you guys are muted up there, just so you know.
Thanks for pointing that out, Brian. Yeah. So I'll go ahead and pull back up one of the ones I had, which is probably one of the most interesting ones. This is actually a graphic of Explore Fall. That is a citizen science website that produced fall foliage maps. I've actually discussed, I've had conversations with the creator and know him personally, and it's some really solid work. This is publicly available. If you go to explorefall.com, they have some great resources. For me personally, I know my work will be published on Mount Washington with my internship, and you guys can also, if you hear from Radio Vermont, if you're in that region, you'll be able to listen to those forecasts that our observers will be giving in the coming weeks here as we get to fall.
Excellent. Yeah. So if there are any Vermonters in the room or online, keep an eye out with Radio Vermont in the coming months here. So it should be pretty exciting.
What's the time interval change in that graphic?
On that figure? So yeah, Madelynn, I don't know if you can hear that, but what's the time interval that we're looking at? I can kind of see it a little bit, but if you can maybe just express sort of, is it like week to week, sort of like September through October? Is that what, or November? What are we seeing?
Yeah, absolutely. So this goes from September to the end of October into, to the first week of November. So it starts mid-September, September 15th, and the interval is weekly. So every 7 days I have this change. So just to kind of give a weekly progression, that's how foliage is evolving.
Yeah, clearly a lot of changes just week to week with that interval. You can see it very, very clearly. And also I like the color shading matches nicely with probably what we're actually seeing with leaves. Another question online, a question from Mike, who's curious, maybe if, I don't know, I'm not sure who might be the best to describe this. Maybe I'll put Max, because you're currently on shift right now. Maybe could you explain, Mike's curious what a day in the life of an observer or an intern looks like, and what it means to be sort of on duty. And I don't know, maybe the best representation of this is, what did your day look like today? Today's Thursday. It's the second day of your shift, your first sort of full day. And what did your day sort of look like today as an intern?
Yeah, so today was a little bit atypical just because we are wrapping up our projects, and also we had storm scouts come in, which took up some of our tour slots. But essentially what a normal day on the summit looks like is we wake up at around 6:30 and get ready to report up here to do radio call at 7 in the morning. We report the weather forecast to all of the wonderful HUTS systems here from the ANC crew. Give them the current weather conditions, and also give them what we project for not only the rest of the day, but also up to a 48-hour forecasting period. And then between that time, we eat breakfast and do a lot of our research. Most of our research is done in the morning, at least on our shift, because that is when we actually have the most uninterrupted time to do it. And then we start to do our tours throughout the day. So we have 3 tours a day, at 11, 1, and 3. And yeah, we show up to outside the weather room doors and accept walk-ons for the tour if there's availability, or just wait for any of the parties that had checked in. And then once we do that, we give them the wonderful tour through our observatory and then also to the top of the tower. And then after our tour, sometimes we're responsible for producing the higher summits forecast. So yesterday, that's what I did. And we basically do the higher summits forecast for the 48-hour period, and then record the audio message that you get to hear if you ever look at the higher summits forecast on the Mount Washington Observatory page. And then after that, at 6 o'clock, we go down to all have a family style dinner together. It's the only meal that we actually all have together, so it's really special, and it's a home cooked meal made by our volunteers who work really hard on the summit every week. And yeah, and then after that, it's pretty much downtime. We like to fill our downtime by playing video games like Mario Kart and Super Mario Bros. We also go into puzzles. We have a couple of jigsaw puzzles that we're working on currently. We love the White Mountain Puzzle Company. I bought a lot from them this summer. Or we'll watch TV shows, and yeah, it's been a really it's a really fun time to just kind of have some downtime with your the observers. You don't get to really talk to them too much during the work week because I'm so busy. So it's kind of fun to just kind of unwind with everybody and have a good time.
Yeah, thanks, Matt. I think that's a great description, and that's just one day, and there are a lot of other that come up, obviously, and not to mention taking care of Nimbus or a visit from one of our U.S. senators this week, or as was mentioned, the Storm Scouts camp that came up, and many other visitors and occurrences. So thank you for that. This is a really nice question from Douglas that I think is a good challenge for all of you and everything you've learned so far and in your work here as budding researchers. But Doug says, please ask each person what is their #1 takeaway in one sentence with as little scientific lingo as possible. And yeah, we're putting you all on the spot. I think this is a good one. It's just, in a nutshell, how would you describe, I don't know, maybe to like a 3rd grader, what you learned? What's the big takeaway from each of your projects? And I don't know who wants to go first on that if someone feels ready and willing.
I can take it away first, if that works.
Go for it, Ryan.
I think the biggest takeaway from my project is that we get the most extreme rain on Mount Washington in October, in the fall.
There. Oh, well done. Well done.
Yeah.
All right, who wants next?
I'll go. Basically, my biggest takeaway is that we're entering an environment that allows us to have more isolated thunderstorms. That's my biggest takeaway from the research.
Nailed it. Nice job. Madelynn, you're up there. What?
Yeah, for sure. I guess my biggest takeaway is that fall foliage is definitely still a field that has a budding field that has a lot of research left to go.
Oh, and you got a pun in there too. That's really good. Do you want to share in front of the camera and microphone?
I guess to boil it down, there's a lot of things that affect the amount of snow on Mount Washington.
Yes, there you go. You guys nailed it. Well done. Great question, Douglas. Really appreciate that. I think we saw some good learning taking place right there. And Douglas gives you all kudos, by the way. Other questions from folks here in the room as well? Anything else that bubbled up? Because there's plenty online as well. Well, here's one that seems timely. It's a nice question from Kristen, who's asking, any thoughts about how the smoke from the fires that seem so prevalent these past several years might also impact the full foliage onset or intensity? And Madelynn, I don't know. I mean, was that one of the parameters that you've even considered, like particulate matter or pollution that may affect foliage? I don't know how that might impact. Certainly that we know that there to be impacts from acid rain and some other pollutants, but did that come up at all, or is that a portion that has come up in anyone else's research of late?
Yeah, absolutely. That has come up in my research a little bit, especially it's still, like I said earlier, fall foliage is definitely a budding field. There's a lot of research left to do. Yeah, it definitely lower air quality definitely does affect the tree health overall. And when we have unhealthier trees, we get we can have delayed fall foliage, or we can duller fall foliage, or earlier fall foliage. The results have kind of varied on the timing of how that air quality can play into that. But it definitely does have an effect, and there's ongoing research onto what that effect may be and what the extent it is.
Excellent. Thanks, Madelynn. I appreciate that. And then I think we may have time for just one more question. And Mike, this one might be a nice one for you as well, if you wanted to come on over. I mean, John's asking a question here, just sort of more broadly, the responsibilities of weather operations. Oh, buzzing thing again. Do weather staff initiate emergency weather notices if they see something developing, or is the weather station more often the recipient of emergency weather notices from other official weather stations? You want to come on over and answer that one, because that's a good one.
Yeah, absolutely. Yeah, as far as what we do for our weather operations, we don't necessarily specifically issue any advisories, watches, and warnings, those sorts of things. We are usually the recipients and then sort of the amplifiers of that information. So if there's a particularly notable event happening and the National Weather Service is issuing watches and warnings of that nature, we'll include that in our forecasts, those sorts of things. So we don't necessarily issue anything ourselves, but we're always in all of our forecasts trying to amplify the information that's put out there by the best resources, which for weather forecasting is by far the National Weather Service.
Would the one exception be, what is it, wind chill warnings? Do we actually produce
so there is
wind chill
there is that
specific to Mount Washington?
It is specific to Mount Washington, so that's a very unique thing that we do. That's a good dimension, that we do issue wind chill watches and warnings. Essentially, if we're dropping below a certain criteria, we'll issue that just for the higher summits of the White Mountains. National Weather Service just recently tweaked their definitions of extreme cold warnings, so I'm not quite sure how those align with what we do, but we have our own particular criteria for that.
Good one. I always thought that was a fun fact, because that's the one exception that I maybe knew of. But thanks, Mike, and thanks to all of you, everyone who joined here tonight, everyone who joined online. Really appreciate. Really a fantastic job, all of the interns here. Really great presentations this evening. I know you worked so hard, and your research projects, as we all learned tonight, was just one piece of all the responsibilities you had in this learning journey. So for everyone who joined tonight, I hope you enjoyed tonight's free program. If you're feeling motivated to support, well done. If you're feeling motivated to support free programs like this, we certainly encourage you to make a donation over at mountwashington.org. If you have thoughts about tonight's program, hey, those of you in the room, you're welcome to stick around, share a little feedback if you'd like. We are going to send out a survey to folks who participated online, so keep an eye out for that. We certainly appreciate any and all constructive feedback. And then finally, stay tuned for any future programs. We're here in person in North Conway this month. We're going to be taking a slightly different structure for our Science in the Mountains programs, where we're going to take it a bit more quarterly. And then in the winter, we'll probably return to a primarily virtual series. But we're hoping to bring Science in the Mountains into communities near wherever you may live, somewhere in New England. So thanks to all of you who joined in person. Thanks to everyone who joined online. And thanks again to all of our presenters. I hope you guys have a great night. And thank you once again. Take care, everybody. Bye.